And now it's time to stress you out. That's right, today is going to be all about stress. Le Chatelier's principle, or factors that affect equilibrium. Predicting what way the equilibrium will shift when you stress it. Predicting the resulting change of concentration when you stress the equilibrium. And making equilibrium serve your own evil purposes. Because equilibrium is a rate balance, anything that can mess with reaction rate can mess with equilibrium. It's kind of like you're walking on the treadmill. Your little brother or sister walks in the room and cranks up the speed on the treadmill and you fly off the treadmill. Or they turn the speed down on your treadmill and you go walking into the front. So what are some factors that affect reaction rate? Well, first of all, there's temperature. If you change the temperature, you're going to shift the equilibrium. Concentration. If you open up the container and put stuff in or take stuff out, you're going to mess up the equilibrium. Pressure. If you change the pressure and there are gases in your reaction, you're going to mess up your equilibrium. Surface area. Well, you really can't do much with that. So that's not going to impact on our equilibrium at all. What about catalysts and inhibitors? Well, they're going to affect both rates equally. They're going to make the forward and reverse faster or slower exactly by the same amount. So throwing in a catalyst will make you reach equilibrium faster. And an inhibitor will make you reach equilibrium slower. But once you're there, if you add this stuff, it'll have no effect at all, because it's going to have an equal effect on both reaction rates. Now, here's some things you need to know about Le Chatelier's principle. Number one, stress. You're either going to add or remove a reactant, add or remove a product, thereby changing its concentration. Or you can change the temperature and pressure. As a result of that stress, the equilibrium is going to shift in a direction that relieves that stress. Whatever you did by adding a stress, the shift is going to try to undo that stress that you just put in. In other words, you raise the temperature, it's going to try to bring the temperature back down. Increase the pressure, it's going to try to bring the pressure back down. Add a reactant, it's going to try to take the concentration of that reactant back down. So whatever you did to stress it, it's going to shift in a way that undoes whatever it is you just did. Because of the shift in equilibrium, everything is going to change in concentration. Whatever you shift towards is going to go up in concentration. And whatever you shift away from is going to go down in concentration. So here's the technical stuff. If you change the concentration, this is what happens. If reactant is added, then what's going to happen is you're going to have more collisions between your reactant particles, which means the rate of the forward reaction will increase, meaning the reaction will shift forward. If you add a product, then you're going to have more collisions between your product particles, which means the rate of your reverse reaction will increase, a reverse shift. If reactant is removed, you'll have fewer collisions between the reactants. Therefore, the forward reaction rate decreases, making the reaction shift in reverse. If you remove a product, you'll have fewer collisions between your products. Therefore, the rate of the reverse reaction will decrease, and it'll be a forward shift. Does that sound confusing? Let's do some examples and see if this can be made understandable. If you add nitrogen, you'll have more collisions between nitrogen and hydrogen, making the forward reaction go faster, which means the shift will be a forward shift. Now, when the equilibrium shifts, whatever it shifts away from is getting used up, and whatever you're shifting towards is being made more of. So therefore, if you add N2, the equilibrium wants to shift in a direction that uses up the excess N2 that you put in. So N2 will go down, but N2 can't go down unless it also uses up H2. You can't use up your reactants without making more products. So NH3 being a product you're shifting towards, the concentration will increase. And H2 is getting used up as you use up the excess N2. Its concentration decreases. Stress, shift, change in concentration. If you remove NH3, the equilibrium is going to shift in a direction that reverses what you just did. You just removed NH3, the equilibrium will shift in a way that brings the concentration of NH3 back up again. Shift in the forward direction to bring the NH3 back up again. The resulting effect on NH3? Well, you removed it, but now it's shifting in a direction that brings its concentration back up again. What about N2 and H2? Well, you can't make more NH3 without using up your reactants, so hydrogen's concentration will go down. If you remove N2, there'll be less N2 and the equilibrium will shift in the direction that brings its concentration back up again. Shifting towards N2 will bring N2's concentration back up again. But you can't bring N2 up without also bringing up H2 and using up NH3. N2 and H2 are both formed when NH3 decomposes. This should be a double arrow. Bad boy! So the NH3 will decrease as it goes into making more N2 to replace what you removed, and the concentration of H2 will go up because you can't make more of this reactant unless you're also making more of that reactant.